So good afternoon all. Um, so this week's tutorial is basically on BJT differential amplifiers, right? So I hope you have all submitted the tutorial solutions in the appropriate Dropbox. Please make sure that you make all the necessary submissions every week because these are easy weightings that you can gain, right? So let's start with this week's tutorial, right? There's 4 questions, so let's start. Question number 1, a BJT differential amplifier uses a 0.3 milliamp bias current. What is the value of GM of each device if beta is equal to 100? What is the differential input resistance? So we need to calculate both the transconductance and the differential input resistance, right? So when we are biasing a BJT differential amplifier, the biasing current is usually at the emitter end, isn't it? So in that particular case, what happens is to find our IE, we have to divide the biasing current by 2. So our IE in that particular case would be 0.3 milliamp divided by 2, that is equal to 0.15 milliamps, right? And this is my IE, right? This is my IE, okay? So my IE is basically equal to 0.3 milliamps divided by 2, which is equal to 0.15 milliamps, right? Since our beta value is given, we can calculate our alpha, right? That is beta upon beta plus 1. However, it is usually we also assume that alpha is equal to 1, right? Because beta upon beta plus 1, in that particular case, it will be 100 upon 100 plus 1, that is 101. So you can see that you get a alpha value of 0.99, right? It is approximately equal to 1, right? So that is why we are using an approximation representation over here. So just in case, in that particular case, if you are assuming alpha is equal to 1, right? So in that particular case, our IE would be equal to IC. So that is basically our IE is approximately equal to our IC, right? Or if you are calculating your alpha value, that is beta upon beta plus 1, you'll be getting somewhere close to that 0.99 multiplied by 0.15, right? And then you'll get the value. But for our purpose over here for this tutorial, we'll just consider alpha is equal to 1, right? Since alpha value is not given, we'll consider alpha is equal to 1. So if our alpha is equal to 1, our IE will be approximately equal to our IC. So once we know our IC, right, we can basically calculate our transconductance. So our transconductance is basically equal to IC upon VT. So we know our IC value, that is 0.15 milliamps, right? And we know our VT value. So directly substituting into this particular formula, we get our transconductance, that is equal to 6 milliamps per volt. So next is to calculate our RID. So our RID is basically equivalent to 2 into beta plus RE, right? So to calculate our RE is basically VT upon IE, isn't it? Right? So our RE is basically equal to VT upon IE. So if our IE is approximately equal to IC, right? You can see that this, if our IE is approximately equal to IC, it will become VT upon IC. So basically it is the inverse of transconductance, isn't it? So what we can do is we can use this same transconductance, the inverse of this particular transconductance, as the value of our RE. So we know our beta value, we know our transconductance, we can or we can calculate our RE, right? So we know our beta, we can calculate our RE using this particular formula. That would be basically equivalent to 1 upon 6 milli, right? Or 1 upon 6 times 10 to the power of minus 3, right? And we have 2, right? 2 times, in place of beta, if you substitute 100, that would be 100 plus 1, that is 101. That's what we have here. And RE, like I explained, it would be equal to 1 upon transconductance, that is 1 upon 6 times 10 to the power of minus 3. This is because our IC is approximately equal to our IE, right? That is why we are using 1 upon the transconductance value. So our RID in that particular case will be approximately equal to 33.66 kilo ohms. Okay. Moving on to question number 2. a BJT differential amplifier is biased from a 3 milliamp constant current source and includes a 200 ohm resistor in each emitter, right? So our emitter resistance is basically 200 ohms, and our biasing current is basically equal to 3 milliamps, right? The collectors are connected to VCC via a 5 kilo ohm resistor, right? So the VCC is connected via 5 kilo ohm resistors, right? So in this particular case, our RC is 5 kilo ohms, right? A differential input signal of 0.1 volt is applied between the two bases, right? So basically, we are applying a differential voltage of 0.1 volt, right? So one of the terminals will be positive, the other end will be negative, right? So find signal current in the emitter, right? And the signal voltage VB for each BJT. So in that particular case, if you write our IE formula will be basically the differential input voltage divided by 2 upon RE plus RE, right? This is a small RE plus capital RE, right? So this is the formula for our small IE. So just observing this particular formula, you can see that we know our differential input voltage. We know our capital RE or the emitter resistance. We do not know our small RE. So our small RE is basically equal to VT divided by IE. In this particular case, our IE will be the biasing current for each of the transistor, right? So in this particular case, we know our biasing current for both the transistor is 3 milliamp. So if we find the IE for one transistor, that will be 3 milliamps divided by 2, right? So in that particular case, our IE will be 3 divided by 2, that is 1.5 milliamps, right? So our RE is basically equal to VT divided by IE. So in that particular case, it is equal to 25 millivolt divided by 3 divided by 2 milliamps, so that is 1.5 milliamps. So our RE is equal to 16.67 ohms, right? So once we know our RE value from here, we just need to plug in the values over here into this particular formula. That would be equal to 0.1 volt, right? Since our input differential voltage is 0.1 volt, divide by 2 into this small RE is 16.67 ohms plus our capital RE, right? The emitter resistance is basically 200, so there is 200. So evaluating this particular part over here, that is going to give me 0.23 milliamps, right? So once we have our small IE or the AC emitter current, we move on to the second part of this particular question. It says, oh sorry, we haven't finished over here. So we also need to calculate our VBE. So this is where I have this particular example file over here, right? Since you can see my handwriting right on this screen is like really horrible right now. So what I'm going to do is I'm going to show you the formula over here, right? So this is the formula for VBE. So VBE is basically equal to small RE upon RE plus capital RE into VID divided by 2. So in this particular case, our small RE, right? Our small RE is 16.67 ohms and our capital RE is 200 ohms. So what we do is we go back over here, we substitute the values. We know our VID is equal to 0.1 volt. So substituting the values, you'll be getting just let me do this quickly. So you should be getting close to 3.85 milliamps, right? So again, actually I'm using this particular formula. You just need to use this particular formula over here, right? In this particular question, that will be small RE, right? Small RE upon RE plus capital RE, right? Small RE upon RE plus capital RE into VID divided by 2, right? So that will give you your VBE. That would be 3.85 milliamps. So you can see, right? Actually, I have supplied this example file in the Viber group, right? So you can use this particular sample file as a practice problem, right? You can see this particular question is somewhat similar to this particular question. So that is why I have given out this particular file for your practice problem, right? You can use it as a practice problem and see whether you are able to get the answers or not, right? The solution is given over here. You can follow through, right? So likewise, we move on to this move on to part B of this particular question. It says, what is the total emitter current in each BJT? So total emitter current is basically the sum of the DC current plus the AC current. So in that particular case, the bias current, right? So that will be the bias current. The bias current for emitter 1, if you just look at the bias current for emitter 1, that is equal to 3 divided by 2, right? 3 divided by 2. So that is 1.5 milliamps, right? That will be just the bias current. So 1.5 milliamps is the bias current. Plus, right? The input to this particular BJT over here is a positive, right? Isn't it? It's positive. So what happens is that this current, that small IE will be positive, right? So that is plus 0.23. Okay. We have this bias current, and the bias current for this transistor is half of this biasing current, that is 1.5 milliamps, plus this small IE, that is going to be 0.23 milliamps, right? Since it's a positive terminal, we are going to consider this voltage positive. I mean, this particular current positive, right? So summing that up is going to give me the emitter current for this particular BJT, or IE1, equal to 1.73 milliamps. For my IE2 is again, like I said, the biasing current for this transistor will be again 3 milliamps divided by 2, that is 1.5 milliamps, right? And then the sum of this, and some of the current that is flowing in this particular branch, that is due to the negative input of the differential voltage, right? Isn't it? So it's a negative current that will be flowing over here. So in that particular case, what we do is we consider the negative current or negative magnitude of this particular current, IE. So in that particular case, it will be 1.5 plus negative 0.23, that is 1.5 minus 0.23. So we are going to get 1.27 milliamps as our IE2. Okay. So we have calculated our IE, right? The total emitter current for each of the BJTs. Next is part C. What is the signal voltage at each collector? Assume alpha is equal to 1. So the signal voltage is each of the collector current. That means VC1 and VC2, right? So our AC voltage outputs VC1 and VC2, or the small signal voltage output at AC1. Just excuse me. Okay. So for VC1, that is equal to there will be the small signal analysis VC1, right? So that is equal to negative, right? This is, you must have learned this in your labs as well, and in your lectures as well. The input voltage, what happens is actually the input voltage. There is a phase difference between the base voltage and the collector voltage, isn't it? The input voltage and the output voltage. There is a 180 degrees phase difference. So what we do is, if the input is positive, so our VC1 should be negative, isn't it? That will indicate it's a 180 degrees out of phase, isn't it? So that is why we use negative, right? So in that particular case, is this, right? Yeah. So that is going to be negative. So VC1 is basically going to be equal to negative, right? Negative indicating the 180 degree phase difference, times negative of IC times RC, right? So that is going to be the formula for VC1. So directly substituting the values, our IC1 is basically equivalent to, since our alpha is 1, so our IC, our small IC, is equivalent to our small IE. So that is 0.23 milliamps, right? So our IC value is 0.23 milliamps. So negative 0.23 times our RC value is 5 kilo ohms. That is going to give us negative 1.15 volt. Similarly, if you do it for VC2, so for VC2, it is going to be, again, the input voltage is negative, so our output will be positive. So again, the formula will remain same. That in that particular case, it will be just IC times RC, right? In place of this negative, it will be just positive, right? It will be just IC times RC. So in that particular case, you should be getting 0.23 milliamps times 0.23 milliamps times, oh, sorry. Yeah, that will be 0.23 milliamps times 5 kiloohms. That will give me a positive voltage of 1.15 milliamps, right? Moving on to say last part of this particular question, it says, what is the voltage gain realized when the output is taken between two collectors? So the voltage gain, we have to calculate the voltage gain. So the voltage gain is basically equal to voltage, the output voltage divided by the differential input voltage. That is equal to, we know output, we know input voltage, that is 0.1 volt. We do not know output voltage between these two terminals, isn't it? So in order to find our output voltage, the differential output voltage, that would be, since this terminal is going, the first thing is to calculate our V0, we have to identify the positive and negative terminals. So you can see that this particular branch, or this particular BJT has a negative input. So our output will be positive. So this is my positive input, isn't it? And this particular output, since it's having a positive input voltage, the output voltage is negative. So we'll be measuring the voltage across these two terminals, isn't it? So in that particular case, it will be VC2 minus VC1, isn't it? Or the voltage difference between these two terminals, right? So in that particular case, that would be 1.15 volt minus 1.15 volt. So if you do 1.15 volt minus negative 1.15 volt, you'll be getting 2.3 volt. So once we have identified our output voltage, that is 2.3 volt, so we can substitute it into this particular formula, that is to output voltage upon input voltage, that is equal to 2.3 volt divided by the input voltage, that was 0.1 volt. So our gain, or the differential gain, is basically equivalent to 23 volts per volt, right? Don't forget the units. The units are really important, right? So in your short test, please, in your examinations also, please remember to use the units, right? Moving on to the third question. Third question is, find the voltage gain and the input resistance of the amplifier shown in figure 2, assuming beta is equal to 100, right? So it says we need to find the voltage gain and the input resistance, right? So voltage gain is basically equivalent to, right? Voltage gain for this particular, if you visualize this particular question over here, this particular diagram, figure 2. So this is the figure that is being talked about, right? So in this particular case, our voltage output is basically due to the RC and the RE values, isn't it? So in this particular case, you can see one of the resistor values aren't present over here. The collector resistance value is not present over here. So that is basically equivalent to 0, isn't it? So in that particular case, it will be the total resistance, right? Total resistance. So it is alpha times total resistance, the total collector resistance. So if there was another resistance over here, the collector resistance of same value, it would have been 2 RC. So, but however, in this particular case, there is only 1 RC. So it will be alpha times RC upon the total RE, or total emitter resistance, due to the thermal resistance and the emitter resistance. That would be small re plus capital RE, right? So yeah, so that will be capital RE, right? So this will be for one transistor, right? For one transistor. So what happens is the total emitter resistance for transistor 1 and 2 will be twice as it, right? Because this side has same emitter resistance, this side, this side has same emitter resistance as this particular side as well, right? So the small RE over here is also equivalent to the small RE over here. Both the sides are equivalent, right? So the formula for the differential output voltage is basically alpha times RC upon 2 into small re plus capital RE, right? So that will be the formula for our that will be the formula for our output. That will be the formula for our voltage gain, right? So in this particular case, we know RC, we know RE. So our RC is 20 kilo ohms. Our RE is 100 ohms, right? We need to find our RE. So in order to find our RE, right? To find our RE, we need to find the biasing emitter current for each individual transistor. So in that case, it will be 1 milliamp divided by 2. right? So my IE or biasing IE1 in that particular case will be half milliamps. So in that particular case, to find our RE is basically equivalent to VT divided by I by 2. So that is going to be equivalent to 25 millivolt divided by 0.5 milliamps, right? That can be that can also be written as 0.05 volt divided by 1 milliamp, which is equivalent to 50 ohms, right? So we have our RE value. We know our RC value from the diagram. We know our RE value, our capital RE or the emitter resistance. So we can substitute it into this particular formula to find our voltage gain, right? So that is alpha times RC. So alpha times RC. So our alpha value, in this particular case, right? So alpha times RC. So alpha is alpha value is not given, so we'll assume alpha is equal to 1, or even if we calculate our alpha, that will be close to approximately equivalent to 1, right? So in that particular case, our alpha is, let's say our alpha is, or let's assume our alpha is equivalent to 1. Alpha times RC, right? So alpha times RC. So in that particular case, if our alpha is 1, so it will be just RC. So our RC value is 20 kilo ohms. Divide by 2 into 2 times RE plus 2 times emitter RE, right? The emitter resistance. So in that particular case, it will be 2 times 50. So that is 100 plus our emitter resistance is 100. So that is 2 times 100, that is going to be 200. So our differential gain is basically equivalent to this, right? 20 kilo ohms upon 100 plus 200, that is equivalent to 66.67 volt per watt, right? So yeah, so don't forget about the units, right? So next is we need to also find the input resistance of this amplifier, right? Of this particular BJT, right? Or the differential amplifier. So the differential amplifier, again, I'll just give you a short way of remembering this. It is basically equivalent to beta plus 1, right? Beta plus 1 upon this particular denominator, right? Beta plus 1 times 2 RE plus 2 emitter resistance, right? Twice the emitter resistance. So we know our beta, that is 100, right? We can substitute beta over here, that is beta 100 plus 1, that is going to give me 101. And the other bracket is 2 times RE. So 2 times RE is going to give me 2 times 50 ohms, that is going to be 100. And 2 times capital RE is 200, right? So basically you can use this particular value over here, that is 101 times 300, that is going to give me input resistance of 30 kilo ohms, right? Okay. Let's move on to the last question, right? Last question, it says question number 4, find the voltage gain in the input resistance of the amplifier in figure 3, assuming beta is equal to 100, right? So again, we need to find our voltage gain in our input resistance. Again, this is the second diagram that is given, right? So let me erase this. This was for previous question, previous part. Again, we just need to derive the formula for our voltage gain. So voltage gain is basically upon voltage output upon voltage input. So that is basically equivalent. Our voltage output is at the collector end. So that will be alpha times alpha, right? Alpha times the collector resistance. That is, in this particular case, we only have one collector resistance again as well, isn't it? So the total collector resistance in this particular case is just 1 RC, isn't it? So we'll just write RC. Total collector resistance in this particular case is just 10 kilo ohms, or just 1 RC, right? So we'll just use 1 RC. So alpha times RC. If there was the same valued resistance over here, let's say 10 kilo ohms resistance was on this particular side as well. So we would have used alpha times 2 RC, right? So in this particular case, there's only 1 RC. So we'll be using alpha times RC. And then the total resistance from here till here. So in this particular case, we use this particular formula, isn't it? In that particular case, you can see over here, it was 1 RE, right? It was again the resistance from here till here goes up till here. So there was a small RE across this particular BJT, right? Across VB, across B and E, across B. Sorry, excuse me about that. There was a small RE, right, present due to this particular BJT over here, right? Since these two resistance are identical, these two BJTs are identical, so the small RE over here is also equivalent to this small RE over here, right? So that is why we use 2 times RE, right? 2 times small RE, right? 2 times small RE. And you can see the emitter resistance over here is again symmetrical, so 100 and 100. So that is why we use 2 times the capital RE. So basically, whatever resistance we had, it was the sum of the resistance over here across this, right? There is the same thing that is going to be done over here as well, right? That means we need to find the total resistance over here. So in that particular case, it will be RE plus whatever the resistance that is being shared by both the transistors, right? That is 200. So that would be 200 plus again the other RE, right? So since the transistors are identical in differential amplifiers, we use identical transistors. It is going to be RE plus 200 plus RE. So let's write RE, right? 2 times small RE. This value is alpha, right? This is 2. Plus this emitter resistance that is being shared. So it will be just RE, right? So we know RC, we know our RE. We need to find our small RE. So from this, our small RE could be found using this particular formula, right? This particular formula. Not this one. This particular formula, that is VT divided by IE. So you can see the bias current for one transistor is already separated, right? So one transistor has 1 milliamp, the other transistor also has 1 milliamp. So the RE for this transistor is equivalent to the RE for this particular transistor. So our RE is basically equivalent to 20 millivolt, right? Our RE is a formula VT divided by RE. So RE, our VT is 25 millivolt divided by 1 milliamp. That is going to give me 25 ohms, right? Okay, 25 millivolt divided by 1 milliamps, right? Using this particular formula, we get our RE value, that is 25 ohms. Next is, what else do we need? Right, I'm going to erase this particular formula. So now we know our RE, right? Our small RE is 25 ohms. Our capital RE is 200 ohms, and our RC value is 10 kilo ohms. We know our alpha value is 1. Okay, our alpha value is 1. Since the alpha value is not given, we will assume our alpha value is 1. And we can substitute all the values in this particular formula. Again, that is basically, if our alpha is 1, so it will be 10. Our RC value is 10,000. So 10 times 1,000 upon 2 times RE. So 2 times RE is 50, right? 2 times RE is 50 ohms plus the shared RE is 200, right? So evaluating our differential voltage gain, that is going to be equivalent to 40 volt per volt. Don't forget about the units, right? Then finding our input resistance is basically equal to beta plus 1 times this particular value over here that we have. Like I said, we just need to multiply with the whatever value that we have over here, or the total resistance across from this BJT to this particular BJT. So in that particular case, 2 times RE is again 50 plus the shared RE is 200. So it is 50 plus 200, that is 250. And beta plus 1 is 101. So that would be 101 times 250. So our RID is approximately equivalent to 25 kilo ohms. Okay, I hope that is clear with everyone. Okay, so don't forget about the units. And if you have any other queries, you can raise it. You can send me the queries, right? And we'll end this particular session over here, and we can take your queries after this. Thank you.